Good day, everyone. My name is Besario, and together with my partner Bjorn Joseph Labata, we are going to discuss specifically about isothermal and adiabatic thermal processes using an ideal gas. At the end of our discussion, students are expected to first, understand isothermal and adiabatic thermal processes. Second, differentiate between isothermal and adiabatic thermal processes. And third, solve problem using the formulas for the thermal processes using an ideal gas. In this presentation, we'll focus on the isothermal process. So what does it mean to be isothermal? Iso means the same and thermal means temperature. Thus, isothermal means the same temperature. It is a process in which the temperature of our closed system remains constant throughout the entire duration, while other properties such as pressure and volume change. To understand further, we are going to apply this to a realistic system that undergoes this process. Now, I want all of you to look at the picture over here. This is what we call a piston. We can observe that this is a metal container, and metals are good thermal conductors. You put in hot water at a particular temperature and you keep that hot water flowing around while maintaining its temperature inside of the metal container. For pressure and volume, in this picture, if we reduce this pressure slowly by not applying force or pulling the top of the container, the volume will increase. Or if you push the top slowly, which means increasing the pressure, it will result in reduction of its volume. And during that process, you maintain the same temperature all the way around. That will give you a good approximation for an isothermal process. Temperature doesn't change, so in the scenario, it is maintained by that hot water bath. Now, let us look over our PV diagram. Every point in the PV diagram can be assigned a coordinate, and the coordinates are volume and pressure. If you look over here, these are the V1, P1, and can be also called as the initial volume, and V2, P2 are final volume in an isothermal process. In this process, since we are specializing in ideal gases, there's the ideal gas law, which is PV is equals to nRT. If we want to plot the pressure, we'll have to divide both sides of this equation by the volume. So it will become PV over V is equals to nRT over V. Cancel out the V and we will come up to PV is equals to nRT over V. So how does the pressure vary with volume? First, we must know that the N, R, and T in this process are constants. The number of moles is constant because the number of particles inside the system is not changing since there is no flow of matter in and out. The R is gas constant and the T for temperature is constant since this is an isothermal process. Therefore, the pressure is like 1 over V. And according to Boyle's law, the pressure and volume will be inversely proportional if the temperature and the number of particles, or N, are constant. Thus, our PV diagram is going to look like a rectangular hyperbola. If you can notice in our diagram, we can see a solid red line in the graph which is called an isotherm, meaning constant temperature, and represents the relation between pressure and volume when the temperature is held constant. So as the volume goes to 0, the pressure goes to infinity. And as the volume goes to infinity, pressure goes to 0, since pressure and volume can change contrary to temperature. Since P and V are free to change, work can occur. In this process, the piston can move up during isothermal expansion and down during isothermal compression. If the final volume is greater than the initial volume, meaning there is expansion, we get a positive amount of work done by the system. Contrarily, when the final volume is less than the initial volume, also known as isothermal compression, the amount of work done by the system is negative. Around the system, heat is applied or exists. So, when we use the isothermal condition and the ideal gas law together, we can observe that the internal energy doesn't change. How can we summarize that? That would be delta U is equal to 0. If it is an isothermal expansion or compression of an ideal gas, the work is equal to nRT times the natural log of V final over V initial. So this equation is set up to give us the proper sign for the work as well as if it is expanding, or if the ideal gas is compressing, assuming that its temperature is constant, since we are talking about an isothermal process. Alright, I hope everyone is still awake because now we are going to solve a sample problem with me. 2 moles of the monatomic gas argon expand isothermally at 298 Kelvin from initial volume of 0.025 cubic meter to a final volume of 0.050 cubic meter. Assuming that the argon is an ideal gas, find A, the work done by the gas, B, the change in the internal energy of the gas, and C, the heat supplied to the gas. By analyzing the problem, we can read the words isothermally and ideal gas, big keywords in this sample problem, so we can use the work equation that we got. We have the following given. 2 moles for N, temperature will be 298 Kelvin, and our initial volume is 0.025 cubic meter, and the final volume is 0.050 cubic meter. In the problem, we are tasked to solve for A, the work done, B, the change in internal energy of the gas, and C, the heat supplied to the gas. Now to calculate the work done, let us use work is equals to nRT times the natural log of V final over V initial. We are going to substitute the given, then solve, which leads us to 3,400. What's the unit? Of course, our unit is joules, so it would be 3,400 joules. So we can observe that the final volume is greater than the initial volume, so our answer will be positive. Therefore, what is happening in our closed system? That the gas is expanding, and we can say that it is an isothermal expansion. For the change in internal energy, the word monatomic gas in our problem becomes important. If you remember from our previous discussion, for a monatomic gas, we can calculate the internal energy U with this 3/2 nRT. If we want the change in internal energy, the N and R are going to be constant, so it is 3/2 nRT final minus 3/2 nRT initial. But what's the difference between the final and the initial temperatures? None. So our change in internal energy is 0. For the heat supplied to the gas, using the first law of thermodynamics, delta U is equals to Q minus W, we are going to transpose and add W on both sides, so we will have Q is equals to delta U plus W. We're going to substitute the given. 0 for the change in internal energy plus the work done, which is 3,400 joules. Then we will come up to a positive 3,400 joules. We can conclude that in this situation, from 0.025 cubic meters to 0.05 cubic meters, you need to add 3,400 joules of heat to our closed system. And in this system, an isothermal expansion is occurring. Alright, we're done. So here is our problem. Pause if you like. And here is our solution. So that is the condition of an isothermal process using an ideal gas. Now let us all proceed to learn about the adiabatic thermal processes, which will be discussed by our next reporter. Thank you.
As we know, heat, temperature, and the external environment are factors responsible for the flow of heat from one system to another. Changes do take place when heat is transferred. And this process in which no heat transfer takes place is known as the adiabatic process. Good evening, my name is Joseph Labata from BSN Science SC12, and tonight I'm going to tackle more about the adiabatic process. We're going to ask, what is the adiabatic process? How it differs from the isothermal process? So the adiabatic process is defined as a thermodynamic process in which there is no exchange of heat from the system to its surroundings, neither during expansion or during compression. With that, the adiabatic process can be either reversible or irreversible. So we've already talked about the reversible adiabatic process and the irreversible adiabatic process, but now I'm going to talk about what is an adiabatic expansion. The adiabatic expansion is defined as the expansion in which there is no heat interaction of the system with the surroundings and work is done by the system and at the expense of its internal energy. So, if we talk about earlier what is the adiabatic expansion, now I'm going to discuss or explain to you what is the adiabatic compression. So the adiabatic compression of the air is defined as a compression in which no heat is added or subtracted from the air, and the internal energy of the air is increased, which is equal to the external work done on the air. The pressure of the air is more than the volume as the temperature increases during compression. The adiabatic process is a thermodynamic process in which there is no heat transfer involved from in or out of the system. Adiabatic expansion is defined as the expansion in which there is no heat interaction of the system with the surroundings and work is done by the system at the expense of its internal energy. So the adiabatic compression is that compared to adiabatic expansion, adiabatic compression of the air is defined as the compression in which no heat is added or subtracted from the air. Yes.
Then we are tasked to find the final temperature. So, with that, we are going to use the formula. The initial temperature, the initial volume is equals to raised to R minus 1 is equals to the final temperature and the final volume. Again, R minus 1. So since we are getting the final temperature, so it would be left as blank. So we are going to use this formula. But very first, we have to give its given. So we have the initial temperature is equals to 30 degrees Celsius, but we have to convert it into Kelvin. So we have to just simply 273 Kelvin plus 30 degrees Celsius is equals to 303 Kelvin. So we have the initial temperature is equals to 303 Kelvin. The initial volume is equals to V. Hence, the final volume is equals to 5 or V over 5. With this, since we do have now our given, we will now proceed to the solution. So we have the formula, final temperature is equals to the initial temperature, times the initial volume over the final volume, and R minus 1. So we have to substitute the initial temperature 303 Kelvin, the initial volume V over 5, and 1.4 minus 1. So we have here 303 Kelvin times 5, and we have to subtract this 1.4 minus 1, which is 0.4. So we have to, have its exponent this. Like parang isi-simplify natin sila. So we have final temperature is equals to 303 Kelvin times its simplified product 1.90365. And if we multiply it together, we have the product of 576.81 Kelvin. This is the final temperature of the problem being given.